Hello, everyone, and welcome. Thank you for taking the time today to join our TechXchange webinar. It's great to have you with us. My name is Daniela, and I will guide you through today's session. So before we get started, just a few housekeeping notes here. This webinar is live and is being recorded. All microphones are muted during the session. If you have any questions, please use the Q&A section. You should see the icon in the top menu bar now. We will answer as many questions as possible at the end of this webinar. If we don't have time to cover all of them, we will follow up afterwards. So if you include your name when posting the question, we can contact you directly. In our TechXchange webinars, we aim to bring you expert insights and the latest updates on reciprocating compressor technology and service. Today, we will focus on energy efficiency and emission reduction. And here are the key takeaways you can expect from this session. You will better understand why energy optimization and emission reduction are critical for compressor efficiency and your sustainability targets. It will help you to identify sources of energy consumption, and you will learn how to track emissions within a compressor system. With practical solutions, we want to help you discover how to reduce energy consumption and cut emissions. And I'm very happy to introduce you to the two speakers who will give you those insights. So we have first Madhurya Müller, Sales Manager for Revamp and Upgrade Projects. She brings over 16 years of experience in the industry. Thereof 12 years with Burckhardt Compression, with deep expertise in the design, calculation, and implementation of compressor upgrade and revamp solutions. Joining her here on the right is Richard Stambach, also Sales Manager for Revamps and Upgrades. He has been with the company for over 7 years, but has been in the industry for over 15 years, working in operation and production teams in refineries. So let's get started. And with that, I would like to hand over now to Richard.
Thank you, Daniela. So let's begin with the most important question of all. Why does this matter? Before we look at the solutions, it's important to understand why energy efficiency and emission reduction have become such a critical topic for compressor operators. First, they are the stronger external drivers. Rising energy costs, increased pressure to reduce expenses, and stricter environmental regulation are pushing industries to improve the efficiency of the assets. Second, we need to consider the context and the scale. Reciprocating compressors are among the energy-intensive rotate equipments in many plants. They often operate continuously, 24/7, for decades, consuming several megawatts per hour of operation. Even a small improvement in efficiency can therefore translate it into substantial energy savings and emission reductions over the machine lifetime. And finally, the impact and urgency. The chart on the right side shows that 99.5% of the compressor life cycle gas emissions occur during the operational phase, while only a small fraction come from the manufacturing, production, and transportation. This means that the greatest opportunity to reduce the carbon emissions lies on optimizing how compressors operate through the service life. In other words, energy efficiency is no longer just a technical improvement. It's a business, environmental, and regulatory necessity. With that in mind, let's look more closely where and that energy is consumed and where the emissions actually come from. Start at the top. The drive power enters in the compressor system, and most of the energy is converted into useful gas compression. But part is lost through friction, heat generation, mechanical efficiencies, and leakages. In many cases, a significant portion of the gas being compressed is recirculated within the system, meaning energy consumed to recompress the same gas without contributing to the process. And there are two different types of emissions. First, We have the indirect emissions that are associated with the electricity required to operate the compressor. They are driven by factors such as drive losses, valve performance, friction, heating effects, and operation away from the optimum efficiency point. The second are the indirect emissions. These are the physical releases of the process into the atmosphere through packing leakages, covers, pipe leaks, venting, and flaring. While the volumes might be smaller, the environmental impact can be significant, and they are also related to safety concerns and regulatory risks. The key takeaway is that emissions not come from a single source. They originate across the entire compressor system and contribute to the overall CO2 footprint, operating costs, and product losses, but each require a different set of solutions. Before we recommend a single upgrade, we believe in one principle, and that is measure first. This is BC Activate, our structure assessment for your compressor. It's not a guesswork. We monitor power efficiency to see how much energy you're really using per unit of gas. We run a performance assessment using PV analysis and the simulation. We carry out efficiency analysis to quantify the saving potential, thermal measurements to catch abnormal temperature, and leakage detection to find out the leakage and escaping gas. We put all these real numbers on our CO2 emission calculator. The result is that every recommendations that we make is baked by data, not by your machine, not by assumptions. That brings us to a point that's often misunderstood: the closer relationship between efficiency, optimization, and reliability. It is tempting to think that reliability and efficiency are two separate goals, but they are deeply connected. Look what happens when reliability is poor. Components wear out quickly, you get frequent stops, and those stops mean flaring, burn of gas that you already spend energy compressing. At the same time, components where performance degrades gradually and machine quietly consume more and more energy for the same output. And the third connection, it's maintenance related. As equipment reliability declines, maintenance intervention become more frequent and often take longer. Every maintenance stops creates a period of unavailability, reducing production and potentially requiring gas venting and flaring during shutdown and restart activities. In other words, reliability issues don't just increase in maintenance costs, they directly contribute to emissions and product losses. So how do we actually unlock that potential? Our method is straightforward. We start with on-site data collection with our BC Activate, pressure, temperature, flow, current, PV measurements, all from your running machine. Then we compare the real data against our reciprocal theoretical model, which shows us the gap between how the machine is performed and how it could perform. From there, we build a simulation and optimization plan using our CO2 emission calculator that highlights the biggest CO2 contributors with a concrete action plan and an estimate of the emission reductions and the return of the investment. In other words, you get a quantified and a prioritized roadmap. With this, I will now hand over to my colleague Madhurya for some practical insights.
Thanks, Richard. Hello, everyone. So far, we have discussed where energy losses and emissions originate and how they are measured. Let's look at what can actually be done to reduce energy consumption and eventually improve compressor performance. As mentioned in the previous slide, when we talk about emissions, we are talking about leakage coming directly from components like valves, sealing systems like packings, pistons, piston rings, and rider rings. With operation and over time, these components wear, leading to increased gas leakage, reduced efficiency, and more frequent maintenance interventions. These issues create a chain reaction: higher gas losses, higher power consumption, reduced compressor capacity, increased risk of shutdowns and flaring events. To address these issues, we focus on upgrading the critical compression components. Our solutions include starting with high efficiency valves to reduce the pressure loss, improve overall compressor efficiency, and increase runtime by minimizing wear and optimizing flow paths. Sealing system upgrade with latest design and materials, modern sealing geometries and advanced materials reduce leakage to an absolute minimum while increasing durability and reliability. New Redura packing solution uses optimized ring designs and state-of-the-art material technology to extend component lifetime, improving sealing performance and reduce maintenance effort. Also, packing with the purge and buffer functionality, it prevents process gas from entering the distance piece, while buffer systems capture minimal leakage and direct it to either suction or a safe venting location, greatly enhancing operational safety. The result is not only lower leakage, but also longer component life, improved availability, and better compressor efficiency. For the customer, that means lower emissions, lower maintenance costs, and more reliable operation. Now, capacity control solutions primarily target indirect emissions. A common challenge is that process demand is rarely constant. Many compressors continue to operate close to full capacity even when the process requires substantially less flow. In these situations, energy is being consumed without creating value. There are several ways to match compressor output more closely to process demand. First is stepwise capacity control using suction valve unloaders and clearance pockets. Here, it enables discrete capacity reduction in steps. It is simple and robust solution for stable operating ranges. Another way capacity can be controlled is via a variable speed drive. It allows continuous adjustment of compressor speed and matches output precisely to real-time process demand. For applications requiring greater flexibility, reverse flow control can provide stepless capacity adjustment. Here it is achieved by unloading suction valves during the compression stroke, and it prevents unnecessary compression work. And also it reduces energy losses at low load conditions. The benefit is straightforward. The compressor only delivers what is actually needed by the process. This way, it can create significant energy savings. For example, a 5% reduction in power consumption on a 2.5 megawatt compressor, which is operating at 8,000 hours annually, it saves approximately 1 million kilowatt hours per year. Let's look at a few practical examples, starting with a customer who was primarily focused on leakage reduction and regulatory compliance. So this non-Burckhardt compressor was installed at a refinery and was experiencing significant leakage and reliability issues. Not only were the compressor components like valves, sealing systems were facing problems, there were strict HSE requirements that had to be complied with. So rather than continuing to maintain the existing design, Burckhardt took a complete revamp approach to solve these issues. We applied reverse engineering techniques and designed new API 618 compliant cylinders. So the scope included not only the cylinders, but the complete internals like piston ring, rider ring, valves, new piston rod and packing systems, buffer panel, new motor, modern capacity control system integrated with new and updated control panel. The outcome was very positive. Leakages were reduced to zero, reliability improved significantly, and the compressor became compliant with current HSE requirements. This case demonstrates how a targeted revamp can extend asset life while delivering substantial environmental improvements. So that's an example focused on direct emission reduction. The next case focuses on reducing indirect one. So our second example comes from another refinery application. But here the objective was different. The customer wanted to understand whether there was untapped energy savings potential within the existing compressor system. So in this installation, the customer had two 3.5 megawatt compressors. One unit is usually operating while the other is on standby, with approximately 4,000 operating hours per year on each compressor. During our assessment, we found that the existing capacity control equipment, that is the clearance pockets and the valve unloaders, were not being utilized. So this created an opportunity to improve part load efficiency, and we evaluated two options. Option one was relatively simple, reactivating the existing clearance pockets and valve unloader system. This solution required very little investment and could achieve approximately 3,000 megawatt hours of annual energy savings. However, the control range was only up to 40%. Option two involved a stepless reverse flow control system. While this approach required higher capital investment, it could reach up to 25% capacity control range and achieve almost 4,000 megawatt hours of annual savings and maximize the available efficiency potential. This example highlights the value of performing a detailed assessment before making any investment decisions. To conclude, these are our key messages. First, energy efficiency and emission reduction have become key operational priorities, driven by both operating costs and sustainability requirements. Second, before developing and implementing any solution, it is essential to understand where the losses occur. A structured assessment is the foundation for achieving measurable results. Third, there are proven solutions available today, from sealing and valve upgrades to advanced capacity control systems, and from complete compressor revamps to maintenance strategies. We can develop the most suitable solution in each case. So what can you do next? Think about how you can evaluate your compressor systems for energy and emission improvement opportunities. At Burckhardt Compression, we support customers through our BC Activate assessment. This allows us to analyze compressor performance, identify improvement opportunities, quantify potential energy and emission savings, and develop tailored solutions based on your operational needs. The goal is simple: reduce operating costs, reduce emissions, and improve compressor reliability while maximizing the value of your existing assets. And if you're interested in exploring these opportunities at your site, we'd be happy to discuss your specific challenges after this discussion. Thank you very much. Over to you, Daniela.
Thank you very much, Madhura and Richard, for those insights. We hope they were of value to you. It would be really much appreciated to have your insights, whether you liked today's session or not. You will find now a link in the Q&A section, and you also see the QR code where you can access the very short survey. It only takes a few minutes. So your insights are very important to us to improve the further sessions. And yes, if you would like to stay informed about future sessions that we will have, feel free to register here to our distribution list, so you will stay connected and you will receive every information for about upcoming events. And that brings us to the end of today's session. Thank you all for joining and for your interest in this topic. We hope you found the session useful and valuable. And of course, a special thanks here to our speakers, Madhura and Richard again, as well as everyone behind the scenes who helped making this webinar possible. The recording will be shared with you after the session. And thanks again for joining, and have a great day. Hope to see you in one of our next webinars. Goodbye.
Goodbye.
Goodbye. Thank you.